How self-driving cars work. Most of the self-driving cars uses images to decide their action. Like if you see a right turn, you turn your steering clockwise some unit, and if left then anti-clockwise to some unit, and this keeps your car smoothly on the road. Similarly, the car software takes images as input and outputs rotation of the steerings, accordingly with turning angles of the road. When a child learns to recognize a dog, they are exposed to various images and instances of dogs. Through repeated exposure, they learn to identify common features like fur, ears, and tail. Similarly, a model needs to be trained on a dataset of images labeled with corresponding objects. By analyzing these images and their labels, the A model learns to recognize the features that define a dog or, in our case, steering rotations. Now, next step is to do preprocessing of the image data. As we do not need colorful images to get steering values, as it does not add valuable information to the decision making, so the first step is to change them in grayscale image. Second is to get them into numerical table, and final is to transform it into a flattened array. Similarly, transforming all image data points like this. Model is nothing but just random numbers as same size of image vector and name it as weights vector. Now we are done. This is our model. The baby is born, and now if you are lucky with your random numbers, this will drive your car automatically. Let's test this model with a new image, which looks like a left-turning road with label -9. To get the results, you just have to multiply each element of image vector and weight vector and then sum them up, very similar to dot operations in vectors. And we get the result 68, which is far from the original label -9. And we can surely say that it is not a good prediction by the model, which makes sense as model was not trained and solution it gave was totally random. So is there any way to make model better? But better question would be to know how bad is the current state of the model and how much it needs to improve, and that is know by something called loss. Loss is nothing but it is absolute difference between predicted output and actual label. With random weights our model predicted 68, which 77 point less than actual label -9. This means our model is terribly wrong, and now we have to change the weights so that when multiplied and summed with example, it gives -9. Similarly, for all examples, we have predictions as follows for each example. And also the losses for each image example. And overall loss in the end, which tells how the weights has performed for overall images, not just one, and the lower this number, better the model. Now from here training begins, and ask yourself, what can I do in this setup to make the model better? Pause the video and think. I am pretty sure that you thought about changing the weights, and that is amazing. And if we start changing the weight values randomly, you will see the loss and overall loss calculated starts changing. And the goal will be to change or fine-tune the weights such a way that overall loss decreases, which means model is trying to fit all the training examples, which is basically predicting very close to actual label, thus reducing some of the difference with actual labels that you can see in this clip, which I have taken from the interactive website, whose link I will share in the description, where you can also play around with weights. And once the overall loss goes close to zero, you can see the predictions are quite accurate and close to actual labels. And this means that the model will definitely keep your car on the road. Like first example, the actual label is 5 and prediction is 1, which is very accurate as compared to untrained model, which had random prediction of 39, and the other predictions are almost equal, like zeros, 6 and -7. And if you fine-tune the weights more, then you might get more better results than this. Also, if you remember the first left-turning image we predicted with random untrained weights which performed terribly. Now let's try to predict this unseen image with new trained weights and see how much we have improved. As we can see, the prediction is amazing, very close to the actual label -9, and the best part about this prediction is that it is completely on unseen image which did not participate in training or in fine-tuning weights, and yet it predicted quite well. And voila! We are done at this our model. These are the golden numbers which has all the information about controlling the steering for different turns. But if you notice, the way we have changed the weights is not optimum. It is more like trial and error iteratively, but the better way to do this is through an automated algorithm which takes image, vector, and labels as input and gives out tuned weight as output. And that is called gradient descent. So this is how we create an autonomous self-driving car, and in next few videos we will cover prerequisite to understand gradient descent and eventually learn to apply in different machine learning algorithms. So keep subscribed. Before we end this video, I want you to think of a scenario where instead of using random weights, we borrow weights from some other similar training setup like from a self-pilot plane or vice versa, so that we transfer knowledge from one dataset to other, and in most cases we get better results as compared to random weights. Like think of somebody who knows baseball will learn cricket faster and better than a noob sportsman who know no other sports. One thing I missed to address that once we get prediction from model which are basically steering angles, how it is converted into mechanical force. So that would be basically done with an electrical motor which be rotated clockwise and anticlockwise accordingly with prediction labels. With a belt it could be attached to a steering, and by changing the terminals from electrical source, you can rotate in any direction. And a caveat to add that this is a very simplified version of self-driving car algorithm. Just to make you understand the overview, like what is a model, what is dataset, why data is so important, what is law sets. Even you can see the images used over here are small. Usually they have more pixels, but just to make it simpler to understand we truncated the sizes.